Hello and welcome to Maths on the Move, the podcast from plus.maths.org. I'm Rachel Thomas.
And I'm Marianne Freiberger. Last weekend, our friends and neighbours at the Centre for Mathematical Sciences at the University of Cambridge put up a fantastic event, the Mathematics Discovery Day, part of the Cambridge Festival. Our brilliant colleague Julia Hawkins was herding academics and volunteers, juggling props and generally making everything happen at the Centre for Mathematical Sciences, which is also the home of PLUS.
Now, we weren't able to be there this year, unfortunately, but I've got some very fond memories of being at the CMS at the past for the Cambridge Festival. Do you remember some of the times we've been there?
Oh, yeah. Yeah, I have very fond memories, too, of a time when we demonstrated the bridges of Königsberg problem using yoga mats, I think, and we got very sore knees and legs from that.
Yeah, there was a lot of putting down bridges and then picking them up again as they were blown up. But it was really fun, and we had loads of young kids and adults all helping, and we were just one of many interactive kind of demonstrations of exciting maths and theoretical physics that was on display there. And remember, one year we helped our favourite statistician, Sir Professor David Spiegelhalter, OBE, with his excellent demonstrations of the wonders of statistics. And again, he was there in person again this year. If you were lucky enough to go along, you would have got to meet him and hear his great stories. And also our colleagues from NRICH, Liz and Charlie, were giving fantastic workshops for students, and they were really brilliant and really well attended as well.
And right next door to the CMS, the Centre for Mathematical Sciences, is the Isaac Newton Institute, with whom we are very lucky to be collaborating. And you can find lots of content related to what's happening at the Newton Institute on our website at plus.maths.org. Now, as part of their contribution to the Cambridge Festival, they hosted one of our favorite physicists, Ben Allanach, professor for theoretical physics at the University of Cambridge, who gave a talk which was excitingly titled "The Force Awakens: Quantum Collisions."
Now, that wasn't about Star Wars, but it was about Ben's fascinating work in theoretical physics. Now, Marianne, you talked to Ben last year about some exciting news that we first heard about in the summer of 2023, that scientists were on the verge of discovering a fundamental force of nature that they hadn't previously known about.
Yeah, that's right. So we know about four forces. One is gravity, one is the electromagnetic force, and then there are the strong and the weak nuclear forces. And all of them, except for gravity, are explained by the standard model of particle physics.
So if it was true that scientists have discovered a fifth force, that would be a pretty amazing result.
Yeah, Ben told me that it's all to do with measurements that were made at the Fermilab Particle Accelerator in Illinois. The Fermilab muon G-2 experiment looks at how fundamental particles called muons move around in a magnetic field. Now, fundamental particles are the building blocks of nature. A better known example is the electron, but muons are about 200 times more massive than electrons. They're a bit like spinning tops, and they rotate around the axis of a magnetic field. But as they do so, they wobble. And this wobble can be measured to an incredibly high degree of accuracy, 1 part in a billion. But the new Fermilab measurements conflict with what the standard model predicts about how the muon should wobble.
Now, Ben talked about some of this work at the Cambridge Festival on Saturday at the Newton Institute, and about this exciting possibility of a new fifth force. So if, like us, you weren't able to be there for his talk, here's what he told us about it last year. And here's Ben picking up the story about the problem of the wobble.
So what you want to do is to be able to predict that with a theory to a similar level of precision, of accuracy and precision, and then compare the two numbers. And if the two numbers are different, then the theory's wrong, obviously. And because you can measure so many digits, there might be tiny differences between the two numbers, which are due to new physical effects, which you weren't aware of in any other experiment, which have shown up here. So it's what's called an indirect measurement. You're not seeing something directly, but you're measuring some quantity which is sensitive to new forces, new particles which you didn't know about.
So in this case, in these observations, there was a disagreement with the theoretical.
Yes. So actually, the first measurement was in the late 90s, and there seemed to be a significant disagreement then. But the problem is that's one experiment, and always in particle physics, for big claims especially, but actually in general, you really want two different experiments to independently check, because perhaps one experiment made a mistake. Lots of things can go wrong at this cutting edge of research, and you want to be sure before you accept the evidence. So there's been a new, even much more precise experiment made in Fermilab, and they released their first data a few years ago, and they've released more data earlier this year, and that's why this new news came up. And they indeed find a large discrepancy with the theoretical prediction. So it confirms the old result from the late 90s, and it disagrees with the standard model of particle physics. And so you have to add new particles or new forces to the standard model of particle physics that we didn't know about before, in order to get the two numbers to agree, if that's the correct interpretation.
And perhaps we should explain briefly. So you're talking about new particles that might be causing the wobbling of the muon. How do we go from there to a force?
Yes, so we use this framework called quantum field theory. And what quantum field theory, it's the level of quantum underneath ordinary quantum mechanics. It tells you how particles can be created and absorbed. And actually, really, forces are carried by particles, by quantum excitations of particles. So when you see light, one way of describing that is that there are particles of light, photons, hitting the back of your retina and being absorbed. And the electromagnetic force, actually, so magnetism is exchange of these photons. Many quanta or packets of these photons are being exchanged. And so really a force is the exchange of a particle. So if you have two magnets, what's happening that, perhaps you put the north poles together and they repel. What's happening is one of the magnets is emitting a lot of photons or photonic fields, and you can think of them, roughly speaking, as hitting the other magnet and pushing them apart. And they have these particles have momentum, transfer momentum, and push them apart.
So that's how a new particle can also be a new force,
yes,
because it's
exactly.
the force carrying particle.
So the unexplained behaviour of the muon that Fermilab has measured could be down to a new fundamental force carried by a new fundamental particle that's not included in the standard model. But there's a but. The calculations you need to make to see what the standard model predicts the muon wobble should be, these calculations are incredibly difficult, and indeed some of them are actually impossible to do. So there's various things that you can do to overcome this difficulty and this impossibility. One thing you can do is use a supercomputer to simulate the processes that the difficult bits of the calculations describe. These difficult bits are actually quantum processes that happen in a vacuum. You can then stick the output from your simulation back into your calculation. One collaboration which does these simulations is called the BMW collaboration, because they're based in Budapest, Marseille and Wuppertal. In 2020, they published their results, and their prediction for how the muon should be wobbling more or less agrees with theory. So there's no disagreement between measurement and theory if you're doing your theoretical calculations the BMW way, using the simulations run by the BMW collaboration. But these calculations that disagree with the measurements were made in a different way, not using the BMW simulation. Here's Ben again to explain.
What they did was not use this computer simulation. They used instead experimental measurements to estimate the bits that are hard to calculate. So other experiments, low energy electron-positron scattering, you can use in theory to relate their production of pions in particular to this piece that you can't calculate. And so you can do some maths, but turn the measurements into a number which goes into this calculation.
So is this a bit like, say, if I wanted to use Newton's laws of motion to calculate what happens when I kick a football, or I kick a succession of them, and I don't really feel like can't do the calculation for one part of that, so I just actually go and kick a football to measure how it behaves and stick that into the calculation? Is it a bit like that?
Yes.
So it's replacing a hard bit of maths with observation.
Yeah.
Right.
There's a little bit of maths to do on the measurements, but that maths is not difficult, and we understand it. And so you use the measurements, stick it through a little bit of machinery, which isn't difficult, and then you can get a number to put in. Yeah, exactly.
So then basically it's those calculations that involve the theory, but with a bit of data replacing a bit of the theory, that lead to the discrepancy between the theoretical calculation augmented by data and the observation of the muon precession wobbling.
Absolutely, yeah, thank you.
Right, okay.
And recently there's been another measurement of these kicking of the footballs earlier this year, and it disagrees with all the previous measurements. So you can see it's quite a tricky and messy experimental situation. And actually at the cutting edge of science, it's often like this. Things get settled eventually, hopefully. But when you're discovering things, it's tricky, and you don't know exactly where you stand and so on. And so there's an experiment called CMD3 in Novosibirsk in Russia, and they've measured electron-positron scattering into 2 pions. And when you take their measurement, shove it through this machinery, calculate this extra piece, it explains the difference. It agrees both with the supercomputer calculation of the vacuum, and it agrees with the standard model computation. Now, it disagrees with the other experiments that are measuring electron-positron scattering into 2 pions by quite a lot. And in fact, the other experiments that go in, they also disagree a bit with each other. So the experimental situation is quite messy in the theoretical, in the prediction for the standard model.
So what's going on then, do you think? I mean, do you think there's a serious new physics there, such as a new force that people hadn't known about before, that means that the theory as it is wrong because it doesn't include these new bits? Or do you think it's a matter of something having gone wrong in the calculations?
At the moment, we don't know which has gone wrong. But the good news is we will find out which of those options it is in the next few years, because other experiments are going to repeat these measurements with electron-positron into pions, and so they can check which of the experimental measurements is correct. And that situation should settle down, hopefully, and solve whether it's those that are the problem or not.
So this would mean that the problem lies in the observations that are being made in order to plug into the theoretical calculation
for these difficult bits.
So
yeah.
That's the football. So that's like something wrong with the measurement of how a football flies that
yes.
I wanted to stick into my calculation
yeah.
to make it easier. So if that's wrong, then that doesn't necessarily mean there's a new force or some new physics. It just means that bit of the calculation has gone wrong.
Well, it means some other measurements were wrong for some reason, which of course you'd like to know why, and yeah, that would be the interpretation. Now, if you want, so that's the real situation. We don't know, but we will know. But if you're asking for my personal feeling, I suspect that this will mainly be a problem with these measurements of the football. And the reason I say that is because these supercomputer calculations, which ought to be I mean, well, with this one particular BMW supercomputer calculation, which is the only one that's really accurate enough. And so as long as no one's put an error in line 1 or something, then there's no reason to suspect that shouldn't work, that supercomputer calculation. And the new measurement from Russia agrees with that. So I've got a sneaking suspicion that might be the answer. I hope it's not true, because of course we all want to find new physics. And in fact, there's been a lot of work. Many people have worked on, what kind of new physics it could be. What does it mean in terms of, other theories of the universe? And there's been loads of work on that over the years, as well as work on the standard model prediction as well. So a lot of us are sort of rooting for the beyond the standard model explanation. But I've got a bit of a sinking feeling that it might not be. But we have to see. I mean, the data will tell us.
Yeah, but it's very interesting, perhaps for people who are not physicists. I think it's not that well known that what you guys want is actually new physics. So you're not sitting there thinking, I want my theory that I like the most to be completely correct. You're sitting there going, I want to see something new that hasn't been explained yet.
Yeah, because that's really interesting. And then there'd be a whole nother thing to chase in terms of the research and find out about. And it might, whatever we find, will hopefully explain some mysteries that we currently, can't answer. And like there are plenty of those.
Like, what would be your favorite one to have answered?
So, for example, the fundamental, there's a class of fundamental particles called fermions. They've got a certain amount of spin. They make up electrons, and muons are examples of them. But also the particles that make up the inner bits of the atoms, the quarks. They've got a weird pattern of masses. Between the lightest and the heaviest, there's a factor of 1,000,000 in the mass, okay? And they're spread out logarithmically. So one's 10 times heavier than the other, one's 100 times, one's 1,000 times, one's 10,000 times, more or less. And it looks like there's structure there, and currently they're just fixed at random. And you would naively expect that they'd all be more or less the same, roughly. But they're not. So that's called the fermion mass problem. And I think there ought to be a good option for finding out why the theory requires this and how that comes to be. And a potential new particle which could explain this spin wobble might be a kind of crowbar to help to lead you out of the right door in the right direction.
Interesting. So you said we'll find out soon, like in 2 or 3 years, which might surprise people as well, because that's quite a long time in some other way. So why do these things take so long? I mean, what is it about the experiments that takes a long time? Is it that it takes time to gather enough data to analyze it, or? Yeah.
So first of all, these experiments are highly complicated things. The ones that I'm talking about now, they're not 20 meters rings. These are hundreds of meters long accelerators, and you got to tune the beams, and sometimes you have funny events and the whole thing's short, or it's quite they're complicated machines with a lot of bits, and they're difficult to run. And the fact is, you need a lot of collisions, so you have to take a year's data or something. Try and run it as much as you can for a year, and often they're run on 24-hour cycles, so people are staying up all night, doing shifts in the night to try and take the data, and then you've got to analyze it, and you want to check everything to make sure you understand exactly what's going on and measure the bits that you don't initially understand, so that you can get a really accurate answer out and you can trust it. Because you have those things called systematic errors, which are basically things that you've missed in the experimental setup. And when you're trying to get a really accurate answer out, as we need for this, you don't want to miss something which will change the final results. So that takes time as well to analyze the data and try and make sure that you've not messed anything up. That can take sort of a year as well. So you can spend a year taking the data easily, and spend a year analysing it and convincing yourself you've got the answer right. Mm-hmm. Even with lots of people doing all of that.
Yeah, amazing.
And 3 years in particle physics isn't a long timescale these times. I mean, the Large Hadron Collider was conceived of in the 80s and finally came into being in the 2000s, and it's still running now and will run to the late 30s at least. Yeah, you need a lot of data, and so, you know, decades are often these days a normal timescale. That's why I'm saying that 2 or 3 years is quite short for us.
Yeah. Is there anything about this that will make a difference in sort of application way at some point? Is there anything that you could see on the horizon where it's the discovery of this kind of potential bit of new physics might have something application?
Application to society?
Yeah.
That's a good question. Currently, no. We're all, the thing is, we're all focused on just finding out at the moment where, you know, how the universe is and how it works and so on. Those kind of applications tend to come later because, I mean, the kind of burning issue for us is this a new particle? Is it a new force? Once you found it, then, you know, you might start thinking of some applications. So if you go back 100 years up the road at the Cavendish laboratory, J. Thomson was discovering the electron, actually over 100 years. I don't think he had any idea when he created it that it would underlie the theory of electronics and CD players, or, you know, whatever, or you know, Spotify and etc. So that tends to come a bit later after the discoveries, and we're in that position. I mean, there's been no, as far as I know, there have been no industrial or technological applications thought of yet. But
so it's a bit like pure mathematics. You will have to wait sometimes for it.
You have to wait, that's right.
So, as Ben said, we're going to have to wait to find out if this is a new force, and it may not be one, and we may never find a new force. But what this conversation with Ben has given us is a fascinating glimpse into life at the cutting edge of physics, and it's hard work, both intellectually and experimentally, and the work takes a lot of time and a lot of collaboration and sharing of knowledge between all the different scientists working on these problems. But also it shows us that life at the cutting edge of physics is also incredibly exciting, and I'm always amazed by the fact that what physicists like Ben are often most excited about is the possibility that their theories are wrong. It's such a strange and exciting way to work. So we'll definitely keep our ears to the ground. We'll keep talking to Ben, and we'll let you know when this particular mystery has been resolved. You can find out more about the standard model of particle physics and about quantum field theory, which Ben mentioned, by going to plus.maths.org and entering those terms into the search box. And you can also see lots of content we've produced with Ben Allanach by entering Allanach into the search box, and we've also put links for those things into the show notes. Thanks for listening, and bye for now.